This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, we're online. I have a good number of handouts for you today. They're all going out. They've been posted since yesterday. 2 scheme handouts for material that I just briefly touched on in the last 5 minutes of last Friday, and today, and Wednesday, and Friday still probably will be covering scheme. Your next assignment goes out today. It's not due for a while. I'm not making it due until the Wednesday evening after the weekend. History has shown that the hardest part about this entire assignment is getting the first of the 8 or so functions you have to write written, because that means you have to get used to Kawa, which is the development environment, and getting used to all of the parentheses and understanding how to test your code and things like that. After you get that working, then the assignment is actually, I think, on the easier side as far as 107 assignments go. But recognize that the first function for a lot of people is actually a lot of work. It's not unheard of for some people to spend like an hour to 90 minutes on just the first function, which is like 7 lines of code. And then after that, it's just smooth sailing. But they have to iron out all the rough patches with the first function, and then it gets easier. Okay. We will have discussion section tomorrow. Examples in the section handout for tomorrow are being passed out right now. It's actually a pretty difficult set of problems. They're old final exam questions that I've given in past quarters. But nonetheless, I mean, it's good material for understanding all the little quirks and neat things about Scheme. So I'll let you work with those tomorrow with Ben Newman, who will be teaching it. What I thought I'd do is I thought I'd introduce you a little bit more formally to the development environment and show you how that's going to contribute to your Assignment 7 experience. Okay, so let me bring this down. Create some mood lighting. And let's see where we are with regard to getting everything to fit on the screen. Please, 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 let it fit on the screen. I don't know what that's about right there, the little mushroom. It's a microphone, I think. Oh, there we go. Okay, so let's make sure that this fits on the screen. I'm not sure what people in TV land can see. It looks like they can see my entire computer screen, but it's projecting larger up there for some reason. But as far as I can tell, oh, we're working on it. This is you driving, right? It's actually not a disaster if you just want to leave it. Yeah, 138 is good. That's me up top. Let me just we'll figure it out. Okay. Can everybody see that in the room? See, all I see is Jerry at the bottom. On the lanes and on the pods, where I know I've tested it, also should be work on the myths as well. If you want, you can deal with the scheme environment like I introduced last week, where you can type in 4 and have it confirm that it's 4. You can type in hello and have it confirm that it's really hello. If you want to do things that are meaningful from a mathematical standpoint, you can do that and come back with 21. So this is the shell-like environment where you happen to be dealing with the Scheme language. Now, I don't want to imply that somehow programming in Scheme is all command line driven. It's not. Normally what you will do, you'll spell quit correctly. Oops, sorry, exit. Let me do this. Let me actually, this is huge. Oops. There we go. Okay. That's a little too small for the screen, though. Hold on a second. It's going to have to be this. Okay, good enough. What I want to do is I want to split this. I want to bring this and open up a shell down below, and I'll play with Kawa right here in the lower half. But what I'm going to do up here is I'm going to prepare a little code snippet, the one I finished with on Friday, where I would define in place this thing. If you recall, I called it sorted, and I said it was capable of sorting a sequence, but in the end I said we're going to deal with Scheme's equivalent of a function pointer, which we call a function object in Scheme. And the intent here is that I'm defining this two-argument Scheme function that takes the list, and I'm not committing to a data type. I want it to be heterogeneous by specification, but I don't care whether it's a string list or a list or an int list or what have you. And then I pass in this thing that knows how to compare pairs of elements that reside in that list. And this is what I wrote last time. I wrote, either it's the case that this list is so small that it can't help but be sorted, or it's the case that this CMP, when levied against the car of the sequence and the cdr, I'm sorry, the car of the cdr of the sequence. Now, is that fitting on the screen? Yes, good. There's that. And it's the case that at the same time, sorted cdr of sequence with the same comparison function kind of just works out recursively. Okay, so I can bring this down so you can see it. And that's what I left you with on Friday. Does that make sense? How's that turning out on the screen? I think that actually looks okay on the screen, so people in TV land shouldn't be yelling at me. Okay. I'm going to save this file, and there's a command in Kawa. This is actually common in most Scheme interpreters, where you can load a code file. So in the past, we've prepared .c and .cc files ahead of time, and then gone into a shell and actually typed make to build the executable. What we do now is we actually prepare our Scheme functions in a file that's suffixed by .scm for Scheme, and then we actually load them into the interpreter using this load command that I'm doing down here. Does that make sense to people? Yes, no? Okay, so if this all works out, do that, and then I can type in, is it the case that this list is sorted according to that predicate right there, and hopefully it comes back with a true. And it does, the green T. Okay? If I do this, and I jump all over the place, and I ask whether or not it respects the greater than and equal to predicate, it should come back with a false, and it does. Okay? Make sense to people? Okay, so that's the overarching idea as to how you interact with the Scheme development environment. I give you a .scm file for the Where Am I assignment that's going out today. It has tons of code that's already defined in there, but you're going to go through this, this update the Scheme file, save, and then type load in a parallel Kawa shell, okay, just to kind of bring in whatever code you've most recently written. Okay, does that make sense to everybody? Okay, very good. So there's that. I will put this to bed. I may come back to it. It's fine. But I want to write code on the board because I think it's nicer to create the code than to have it prepared ahead of time. There is this one idiom from C++ with iterators and from assignment 3 with vector map that I want to see the equivalent of in Scheme. Do you understand that if I write this as a function, sum all, actually I don't want to do that, I'm sorry. Let's say, not sum all. Let's say double all. And I give it this list, and without writing code, I think it's pretty clear that the output of this should just be 2, 4, 6, 8. If I have an other function called increment all, and I type in this right here, I expect it to spit out 2, 3, 4, 5. Okay? Do you understand how those are algorithmically similar? They both visit every single element in the list using car cdr recursion. Okay? They both apply some functionality to each car. Okay? But the output is a list of exactly the same length as the incoming list, where each thing that ever served as a car of a cdr is transformed by either the double operation or the increment operation. Does that make sense? Okay. Except for the fact that this is scheme, it kind of screams vector map. Does that make sense to everybody? Okay. Well, it's not like map as a verb was coined for C and C++ purposes. It actually exists everywhere. And rather than doing this, what I could do is I could define a double function, which is not a built-in, but I want to just do this. And I can equate the double operation of an x with that as an expression. I can just do it on one line. I don't have to do it over multiple lines if I don't want to. Okay. I can also define the increment function to be associated with this successor thing. Okay. Does that make sense? There is an operation in pure scheme called map. And it takes two or more arguments. We're going to deal with it as if it's a pure two-argument function. The first argument to map can just be the name of some previously defined function, whether it's a built-in or something you just defined, and then you can specify what list you should be mapping over. Okay, and the result of that call right there, if I typed it in at the prompt, would be 2, 4, 6, 8. If I do the same thing with the map operation, but map incr, this function, over the list instead, then I should get out 2, 3, 4, 5 and be done with it. Okay? Does that make sense? Now, map is a little bit more sophisticated than I'm making it out to be here. I'm making it look like it maps unary functions over single lists. Okay, that will change as we get a little bit more experience with it. But I want you to understand that this is kind of the more functional approach to this up there. If you actually implement that and that, then you're implementing it in terms of exposed car-cdr recursion with both implementations. Does that make sense? Yes, no? Think about what the implementation of that would look like. What I could do instead is I could either use the built-in map, or I'll just pretend for a minute that the map function isn't a built-in and we're going to define it in a second. We can abstract the notion of a map to use car-cdr recursion regardless of what this function turns out to be, okay? And recognize that this can be passed in and caught in a variable like CMP was in the sorted question mark predicate function, okay? So I'm actually going to, I'll give you the full story on map. If you want to, you can map a lot of interesting functions over lists if you want to. If I want to map the car function over a list, I could certainly do it. It better be a list of lists. And that would spit out the list 1, 4, 11. Okay? It's still the case that it transforms the list right there of length 3 into another list of length 3. And it uses this operation right there to figure out how to transform each thing that comes up as a car in the recursion to some element in the final list. Yes? Okay. If I want to do this, map cdr 1, 2, 4, 8, 2, 11. Then I can do that. This would give me the list 2, the list 8, 2, and the empty list. And I once again get a list with 3 top-level elements inside. Okay? The map function, we're not going to implement it this way, but I just want to advertise what it is. It's kind of neat that it can do this. If I want to map the cons function, now cons is different than all the other example, or all the other mapping functions I've chosen in the past because it's not unary. Okay? Well, cdr and car and incr and double are all unary functions, which makes them compatible with a single list to follow it. But if I want to, with the real map, I want to map cons, what I can do is I can provide 2 lists, where one list provides all the first arguments to the cons calls, and the second one provides all the second arguments. So I could do this. And what happens is that the mapping function takes cons and applies it to the 1 and the 4 list to synthesize the first element. Okay? The next element, the second element of the product, has a 2 cons onto the front of the empty list. So the product of this thing right here would be the list 1, 4, the list of 2 just by itself, and the list 8, 2, 5. Okay? Does that make sense? If I wanted to, I could map the plus function over as many lists as I want to. And now I have to add these together, but it would give me 10 and 16. The output is a list of length 2 because all the input lists are of length 2. And this assimilates all of the cars of the 3 arguments into one sum, and then it assimilates all the cars of the cooters into the second argument, and then it realizes that all the lists are empty. Okay? Map is robust enough that if you give it lists of different lengths, if I were to sneak in a third element in the middle list there, it wouldn't freak out. It actually just terminates when the smallest of all the lists reaches its end. Okay, so that particular one would be ignored because the other lists, or at least one other list, is of length 2. Okay, does that make sense to people? Okay, this is the purely functional way of actually visiting or transforming an incoming list normally, or a pair or a triple of incoming lists, into an other list. Okay, that's completely unrelated from a memory standpoint, but it kind of emulates what for each does in the for each algorithm does in C++, and what vector map does from our assignment 3. Okay, we can implement map. I'm not going to implement the binary version yet. I just want to use what we've learned based on the last 10 minutes of last Friday and in the first few minutes of today's lecture to implement our generic map function. I can define map, but I'm not going to call it map because that's the name of a built-in. I'm going to call it my, and I'm going to say unary map to emphasize the fact that I'm implementing a subset of the real map function. Okay, and I'm going to pass in an actual function, and I'm going to pass in, I'll call it a sequence. Somebody asked about ... last time and the equivalent of ... Do you remember that question? Okay, I will use this to motivate the equivalent of ... when I implement the generic version of my map later on. Okay, but right now I'm just dealing with one unary function, and I'm dealing with one list, which I'm calling SEQ. Okay? If it's the case, regardless of what Fn turns out to be, if SEQ is null, then I return the empty list, and Fn has nothing to do with it. Otherwise, what I want to do is I want to cons onto the front whatever I get by applying Fn to the car of the sequence, okay, to the result of calling my unary map, mum, of Fn against the cooter of the sequence. That ends the my unary map, that ends the cons, that ends the if, that ends the entire definition. Okay? Except for the word Fn, which in this case is the name of a local variable that's ostensibly bound to a function. This would more or less be the implementation of double all and increment all that I crossed out up there. Okay, I would have hard-coded double and INCR into 2 separate implementations. I'm trying to abstract away and say I'm going to make this general enough that I can pass in the function that I'd like to be applied to all the elements inside. Okay, does that make sense to people? Yes, no? Okay, so there's that. So this map function, you may say, is it all that useful? And the answer is I think it's kind of useful. I want to show you a different way of actually flattening all of the elements in a list. This is, I think, fascinating how it does this. Okay. If I put this list up here, we're revisiting the flatten problem that we dealt with last time. Do 1, 2. Actually, you know what? let me introduce a couple other functions before I do this. I want to get to this, but I'll get there in 5 minutes. There are a couple other functions that are built in to Scheme that I want you to understand. There are one's called apply, and one's called eval. Eval is easier to introduce, and it's a little bit quirkier. Do you understand that when I type in open paren plus space 1, space 2, space 3, space 4, space 5, close paren, that the interpreter actually reads it, tokenizes it, recognizes that most of them are integers, and it somehow figures out how to invoke the plus function, okay, based on what I typed in. Eval recognizes the fact that everything, at least from whether it's stored in a file or it's typed in at the shell, comes in as a stream of text that needs to be tokenized and evaluated. Okay? If you type in, this looks weird, but if you type this in with that quote there, that suppresses evaluation, right? This would actually come back and it would list this as the output of that operation. Eval, even though this isn't, you wouldn't type this in this way because you would just go with the more direct way of adding the first 3 integers. But if you type this in, like that, whatever its one argument is, it evaluates it. In this case, it evaluates just to the list constant plus 1, 2, 3, because it's quoted. And then it evaluates it as if it were typed in at the command prompt in the interpreter. Does that sit well with everybody? So this would, so slightly less direct means, be a way of actually printing out the sum of the first 3 integers. Okay? Now this is certainly the less common of the 2 operations. Apply is cool. Eval is neat because it advertises the fact that functions and data are really exactly the same thing in Scheme, that everything is expressed as a list. Okay? The function, the code that implements eval in the interpreter for this eval is the very code that gets invoked every time you hit enter, okay, at the interpreter. It reads in the text up to the last matching parentheses, and then it invokes some eval function behind the scenes to get it to produce a 6 or whatever it wants to produce. Okay? Apply is a little bit different. Apply actually allows you to specify which function should be basically pressed against all the arguments that follow. That's another way of computing 6 in a less direct way. Okay, but it won't always be the case that we know that the last argument is the list constant 1, 2, 3. It could be something that's procedurally or functionally generated. Okay? What apply does is it always takes exactly 2 arguments. The first one is always supposed to identify some block of Scheme code. What follows it is always supposed to be a list of the type of data that can actually be levied against by this type of operation. So what apply does is it effectively takes the plus, it conses it onto the front of this thing, and then it evaluates it in this eval sense. Okay, so this would come back with a 6. Okay. More meaningful version, a more meaningful example of where you would use apply. If I just assume that I don't ever have an empty list, if I wanted to find the, let's say the average function, literally I want to compute the average of all the numbers in a list, and I'll just say num list, and I'll assume that they're all doubles so that I don't have any fractions and truncation and things like that to deal with. So I have all of these scores like 39.5 and 40 and 29.5 and all these types of scores we saw in the midterm. If I wanted to, I could write my sumall function using car-coded recursion, okay, to synthesize the sum of all the scores and then divide by the length of the list. Or I could do this. That right there. Okay? That's a more meaningful, less contrived example because I don't know what numList is. And if I really do pass in numList as a list of scores, I have to somehow get the plus to be effectively under the front of that anyway. I could use car recursion. I can't use map because map transforms a list of length n to a list of length m. I don't want that. I want to take a list of length n and produce a single number out of it. Okay? So the apply function is this quick way of actually saying, you know what, I really wanted a plus sign onto the front, or I wanted the function to be the very first element of this list that's right here. So can you just please tuck that under the front and then evaluate it like it was there all along? Okay? Does that make sense? That is a much cleaner way to do it. The drawback of exposed car-coder recursion is that it's asymmetric, and it advertises the asymmetry that's involved in visiting the car of the entire list first, and then the car of the coder second, etc. Whereas both map and apply make it look like all of the elements in a list are peers, and they simultaneously contribute to the overall effort, or the overall computation. When you map the double function over the list 1, 2, 3, 4, 5, all the way through 10, it's like it just dumps out the list 2, 4, 6, 8, etc. Okay, in one fell swoop without actually exposing the fact that there's car-coder recursion involved. The same thing with apply. Rather than actually doing this sum-all function where you recursively, compute the sum-all of the coder and then add with a plus sign to the car of the entire list to that, you just say, okay, num list, all of the elements, you're participating in a plus. Okay, I'm applying the plus to all of you, cooperate and come up with your sum. Okay, and that's the way you actually feel about it, and that's a much more functional way of actually dealing with everything. Okay, the fact that recursion is involved, has nothing to do with the functional paradigm really. That has more to do with the fact that the central data structure in the language is the list, which is a recursive data structure. Okay, that makes sense to people? Okay, as far as eval is concerned, when would you use this? It requires a lot more. The examples are much more complicated. Where I've seen eval used is I've seen eval used where apply couldn't be used. You could imagine applying a plus or a cons or a car or something like that to arguments, right? You can't apply, define, or add, or because they're special functions that don't necessarily evaluate all of their arguments. You understand what I mean when I say that? Like and or, short circuit evaluate, right? So they actually cannot be thought of as normal functions. If you wanted to apply, and I have to use it in quotes, apply and to a list of predicates to figure out whether or not they're all true or not, you couldn't use apply because it really requires this to be a bona fide function, and is not one of those. But you could cons and onto the front of the list and then evaluate it. Okay? Does that make sense? Okay. I've also seen, and this is really sophisticated stuff, I've actually never coded this myself, but I have seen programmatically, the definition of new functions have been synthesized textually. Okay? Do you understand what I mean when I say that? Like you actually can build up as a string something that looks like the definition of a function. Okay? And I mean a definition of a function, something like this. So imagine an algorithm, even though we don't have an example of this here because I think it requires a really sophisticated setting in order for you to need this, but you could imagine this being built up as a string in the language. Okay, or built up as a list rather. So if somehow you can textually synthesize that right there, okay, and use cons and car and coder to construct all of these symbols in one big complicated list, and then pass all of that to an eval statement, you can programmatically introduce the definition of new functions while the program is running. Okay. That's actually a pretty neat idea. Some people would say it's dangerous, that the code would be this self-aware and evolving while it's running. Some people are like, well, that's fine. As long as I'm a good enough programmer and I can handle it, then I'll just be able to use that feature of the programming language. I've never seen it, but I have heard enough and read enough about the contribution of eval and the introduction of evolving functions and functions on the fly in things that involve randomization and things like genetic algorithms where new sentient beings are modeled, while the program is running, and they have different little definitions of how they should execute and respond to the world in the simulation. Okay, does that make sense? Okay, now I'm going to focus on this one because I think it has broader impact on the type of code we're going to write. What I want to do now is I want to revisit the flatten problem now that I know about map and I also know about this thing called apply. Okay. Now I'm going to revisit the flatten thing. That's the car of some list I want to flatten. Here is the coder, sorry, here's another list, another element that I want to be involved in the flattening process, and then I'll have just 10 like that. And you know what the product of the flattening of that should turn out to be. It should be 1, 2, 3, 4, 5, 10, all as pure top-level elements and no intervening parentheses. Parentheses as bookends, okay, but nothing in between other than the numbers. Does that make sense? When we implemented this, first we recursively generated the flattening of this, and then we either consed or appended or prepended this element right here onto the front of it. Okay? In this case, we would flatten this. It wouldn't be very hard, but we would just flatten it and would be very quick about it. And then we appended this to that right there. Does that make sense? Okay, if this had been an atom, then, or not a list, then we just would have conned this onto the front of the recursive flattening. But what I'd like to do is say, I could actually, while I'm defining, this is kind of kooky, but while I'm defining this flatten function, I could implement it recursively. I could recursively flatten all of the elements. Where this gets transformed into a 1, 2, this gets transformed into a 3, 4, 5, and this gets transformed into a 10 just temporarily. Okay? Do you understand how the definition of flatten could involve a recursive call to flatten, but not directly, but via map? Oh, I want to flatten the entire thing. Oh, I should map flatten over the list, okay, and then append all of the things that I get back. Does that make sense to people? Okay. If this is the product of flattening the first element, this is the product of flattening the second element, and I just ensure that this is the product of flattening the last element, okay, then I could effectively get the final product by just appending all of these lists. I could apply, this is going to come back like that if I really use a map call, okay? I could apply the append function to the product of the recursive map call so that it goes through with a thread needle and just basically creates one big sequence out of all of these elements right there, okay? It's really kind of hot. So let's implement this, okay? And then we'll use some leap of faith arguments to defend why we know it's working. But what I want to do is I want to define the flatten function, and I'm just going to give it a sequence. Okay, let's forget about the base case. Okay, we're not even sure what the base case is. Okay, there actually is a base case, but let me just think about the recursive case where if I know I'm dealing with a top-level list of many items, then what I want to do is I want to map this flatten routine that's being defined right here over sequence. Now think about what that does from a leap of faith standpoint. This transforms this list of length 3, okay, into this list of length 3. Okay, if flatten works in this, basically in this involuted way where it actually, the definition of flatten is compatible with itself, okay, it's supposed to transform this into this right here via this one map call, okay? And after that happens, I can apply, not plus, but I can apply the append function to the result of that mapping, okay? It's like taking the list of length 3, pulling the left parentheses in a little bit and sticking the word append at the front and saying, okay, evaluate yourself as if append were there all along. So if I stick in right there the word append and evaluate it, and that's what the apply statement is doing, it will give me one list with 1, 2, 3, 4, 5, 10 in it. Okay? So that's fun, I think, but we only want to do that if this thing really is a list. Okay? If it is the case that the sequence itself is not a list, okay? In other words, if I actually recursively hand a 10 to this thing, Does that make sense? Okay. Then I want to just return the listification of this sequence. Okay. Otherwise, I want this to be the else clause. That balances that. I'm sorry, that balances that, balances that. This ends the if, and this ends the define. Okay. So the base case deals with a scenario when you dive so deeply into the recursion that you've actually arrived at a 1 or a 2 or a 3 or a 5 or a 10. Okay? And you say, okay, now I have to start backing up. But because cons append is involved, I have to wrap them in parentheses so that they behave nicely in the context of the apply append call. Does that make sense? Okay. Think about what happens. This is recursively flattened according to that formula. Okay. It just works out. Same thing with this right here. When it recursively calls flatten against the third element in the sequence, it gets this atom, which is not a list. So it has to wrap these things in parentheses so that when it participates in the apply append call with all of the other peers that were generated recursively, it actually plays nice. Okay? You guys getting this? Okay, very good. Now some people do not like the fact that I gratuitously put these parentheses around the elements, all of them, just for them to disappear. But if I really just want to illustrate how apply and map are working together, then this is still a good vehicle for this function, I think. There's no very easy way for you to look at a list and know whether all the things inside of them are atoms. So the list 1, 2, 3 is different than the list 1, 2, list 3, right? Okay, if I could somehow detect that 1, 2, 3, everything inside is a top-level atom, then I could come up with a more sophisticated implementation here that's a little bit faster. But all I'm trying to illustrate is how apply and map blend in this one example here. Okay, that makes sense? Okay, this is probably the tightest recursion example of recursion you may have seen ever. Okay, in C++, it's buffered with all of this memory allocation. Okay, and it's not so clever in its use of base cases. Scheme is this very expressive, that's the positive PR spin on it. It's this very dense way of expressing algorithms. It's usually as terse as the most articulate person is in describing what the algorithm is supposed to do. Okay, and that is very difficult to look at and understand how it works. Okay, you guys are good? Okay, I have one other topic I want to introduce, and I'll spend a lot of time on Wednesday going over very advanced examples of all of this stuff. But Scheme has been different than everything we've seen before in the sense that it's almost entirely runtime. There's no compile time element to it whatsoever. It is weakly typed, which doesn't mean that there aren't types involved. It means that all kinds of type checking is deferred until runtime. Okay? And if there are problems, then it just presents the problems if it ever comes up while the code is running. There's one next thing actually exists in extensions to C and C++, but it's not part of the core language. I want to think about how we would implement this function. I want to define a function called translate. And I don't mean translate in the linguistic sense. I mean translate in a distance sense. I want to take a list of points in one-dimensional space, so like points on the number line, and I want to shift all of them by a certain delta. Okay? So I'll just say something called points, and I'll say delta right here. Now before I go in and fill in the body here, this is how I want it to work. I want to be able to call translate against 2, 5, 8, 11, 25, and I want to be able to pass in 100. Okay? And I want it to spit out 102, 105, 108, 111, 125, just like that. Okay? I want it to take the list, the first argument that's a list of length n points, and I want it to generate another list of n points where everything's been shifted by some delta amount. Okay? Does that make sense? So you look at this, and given that I just taught you map 35 minutes ago, you may say, okay, well maybe he wants me to use map. And the answer is, I do want you to use map. Okay? But the problem is that there's no clear existing function that knows how to translate a number by another number that's not specified until the function call actually happens. You understand what I mean when that feels a little bit like client data to this map call right here? It's external to the actual thing being mapped over, but it somehow is involved in the product. Does that make sense? So I kind of want to map something right there. I'll just put this big placeholder. And that's supposed to be the function that somehow figures out how to add this number to every single element inside points. I have a very difficult time naming a function right there because I can't call a function called increment by delta because that type of function is going to have to take 2 arguments, not just 1. It would have to take one element that gets bound to the car of the list that it's mapping over, and you'd have to also pass in the 100 to it. Does that make sense? Okay. You guys understand the problem here? Okay. This has to basically either be global data, okay, or it has to behave as global data in the execution of whatever function gets placed right here. Now I'm leaving a lot of space for this thing right here. What you can do in Scheme, and a lot of other languages, but not C or C++, is you can actually embed the definition and scope the definition of a function inside an other function. Okay? This is the way you do that. You erase the placeholder boundary. There's that. You can actually define a function in Scheme on the fly using a keyword called lambda. And lambda is just a gesture to the calculus that backs most programming languages and the way it deals with function call and return. But if I write this right here, just think of it as boilerplate. That means I'm defining a function without giving it a name. Lambda is not the name. Lambda is just a placeholder, meaning it's an anonymous function that I'm defining on the fly. Okay. I am saying quite clearly that this anonymous function takes 1 argument. Why? Because the way we're using map right here, we're mapping over a single list right here. So I need to actually let every single thing that is ever a car of a cooter, okay, actually be passed in and bound to x. The body of this function has to add x to something. It has to take the 2 to a 102, or the 5 to a 105, or the 11 to a 111. Okay, the only way it's going to do that is if its definition can involve the actual value that delta has adopted on this particular call. Okay, does that sit well with everybody? So I can do this, and that ends the lambda definition. So this right here is this anonymous function whose implementation is framed in terms of the one parameter called x and something that is effectively global to its scope called delta. It happens to only exist as a local variable to the outer function, okay? But for the lifetime of this function definition, it exists only long enough for it to be mapped over this thing called points. This is going to adopt whatever value was served the actual translate call, okay? So that if I call this with 100, it constructs an anonymous function on the fly where this is the number 100. If I pass in and call this thing a second time, but I put 1000 there, it constructs a second function, okay, that is, from a memory standpoint, is completely independent of the first invocation of this. And it actually just places a 1000 there as opposed to a 100. Does that make sense? Okay. So that is how that feature works. It is not anything you've seen in standard C or C++. Now it turns out that G++, which is all about extending C++ because it just doesn't like the original language, I guess, it allows you to define inner functions. I haven't advertised it to you. In fact, I didn't know it until a year ago when some student showed it to me. I'm like, oh, let's pretend that that doesn't exist because I don't want people using it. But this right here is actually quite common in the Scheme world anyway. Okay, there are 2 things I want to announce in the last 4 minutes before I leave you go. You actually can explicitly define inner functions if you want to. I actually like both ways. I think that this one, it's kind of jockier. It's like, yeah, I'm not intimidated but I don't need function names, kind of what it's saying. I don't need to wear my seatbelt when I'm coding. So, but there is a more expressive way of doing it that I think is fine. If I wanted to define this translate thing a little bit more, I don't want to say eloquently, just I guess so, a little bit more clearly and be more obtuse about the fact that some inner function is involved, I could define translate I'll just call it SEQ and delta, just like that. I could actually provide an inner definition. Whoops. Keep making this mistake. I can define this inner function internally called shift by, and I can actually give it a name where I actually add delta. Okay. And then right afterwards, I can map this shift by function over the sequence. And that ends the entire define. Now, the reason I don't like this is because it kind of breaks the functional paradigm. I've always equated the definition of some function with one expression, right? Increment is equated with the plus function. Translate over here is equated with the map function. There's always been one expression that was provided as the body of the function, whereas I'm actually providing a sequence here. This is like Roman numeral 1, this is Roman numeral 2. Pure scheme allows you to actually define a sequence of items, okay? And then the expression or whatever the last one evaluates to is what the overall function evaluates to. I don't like this because it isn't purely functional. All of a sudden it takes on this C or C++-like idiom where it constructs a lot of things piecemeal in order to build up the overall answer, okay? But you can define an inner function if you want to, materialize a meaningful name for the short term, define it in terms of local variables and global symbols and local variables plus and delta, and then use the last line to actually define what the map should do or what function should be mapped over the sequence. Okay, does that make sense? Okay, so there's one other thing I should tell you about the define thing. When you write something like this, sum x and y, and you just, it's simple placeholder definition just to illustrate my point right here. That right there is just syntactic sugar for this. Define the sum to be equated with now you may be a little weirded out by the syntax, but the second one is actually much more clear about its association of some function with an actual name. Okay? Does that make sense to people? So that every time you use sum in a call, it evaluates to this lambda function that's compatible with two additional arguments. And then this executes where x and y have been replaced by whatever those two additional arguments evaluate to. Okay? Define actually works. If I want to do this, actually I shouldn't use x. Let's say I want to do like pi 3.14. You haven't seen this before, and I don't want you to use it, but you understand what's probably happening there. It's forever associating capital P, capital I with the number 3.14. This is just basically doing the same thing. It just happens to be associating the word sum, or the symbol sum, not with a constant, I'm sorry, not with a numeric constant or a string constant, but with a lambda constant. Okay? And so every time you use sum, or car, or cdr, or append, or map, or myunary map, or whatever, the actual symbol that's at the front, some plus even, technically, plus and minus and times and all of those, they're all bound to actual lambda functions. We prefer this because it's probably just a little bit more readable and it's more consistent with the way we've learned how to program in other languages, but this is much more clear. I want this, but this is functionally equivalent. This advertises quite clearly that sum is being equated with this thing right here. Okay? Does that make sense? Okay, so scheme really is all about symbol and symbol evaluation and functional evaluation, and right down to the actual definition of the functions and the way they're stored in memory. Okay, so I will cover some more sophisticated examples on Wednesday. You'll also see some sophisticated examples in tomorrow's section as well. So good night.